Okay, onward now to at least much closer to the present day. We're going to talk about Newton's law of gravity, exactly what it says. But first, a little bit of motivation. If we consider Earth as fixed, and we can get in an inertial reference frame that's kind of going along with the Earth, then moon's orbit, and usually it sounds a little bit strange to say moon rather than the moon, but astronomers usually, when they use the name of a planet or moon, they actually treat it like a proper name. So we're going to, just like when we say Earth as opposed to the Earth, people will say sun and moon rather than the sun and the moon. Moon's orbit is approximately uniform circular motion around Earth. It's not exactly, it's slightly elliptical, but it's a pretty good approximation. The same is true for Earth's orbit around the Sun and many other astronomical objects. Their ellipses, according to Kepler's law, are actually not that stretched out or eccentric, as people say. So they're pretty close to circular. So uniform circular motion is going to pay a lot of dividends in talking about the orbits of things. And as we know, there's got to be one or more forces that cause that v squared over r acceleration towards the center of the circle when something's in uniform circular motion. And in the case of gravity and orbits, there's, at least if there's just one really massive object and you're orbiting around it, there's only one force in that case that causes it, and it is gravity. Gravity is that attractive force that the sun pulls on the Earth, just like a string would pull on the ball that that astronaut had, that would keep it in its circular orbit. So this is called Newton's law of universal gravitation. It's called universal because it applies to everything in the universe that has mass. That includes all the planets, all the stars. They're all pulling on each other, but it also applies to everyday things like I have a certain mass and the chair that's next to me has a certain mass, and so we attract each other with a certain force. Everything is attracted to everything else. Now, that force is not very big by everyday standards for everyday sized objects, but because the force only gets bigger as the mass gets bigger, those forces can be really big by the time you get to a planet-sized chunk of mass or a star, and so gravity tends to dominate on the planet-sized scales to larger. Whereas, in our everyday life, actually electric forces can be huge in the lab. We can make really big electric forces between objects, but you tend not to see electric forces playing a big role at the planet size or above, and that's because there are positive and negative electric charges, and they can kind of balance each other out. There's no negative mass that can balance out the positive mass. It's all positive, so it only gets bigger and bigger. In any case, Newton is going to tell us how to calculate how big this force is if we know this mass and then we know this mass. We also need to know the distance between the masses, and here there is a way to apply this to non-spherical masses, but we're going to think of it as applying to spherical masses, m1 and m2, and r measures the distance between the centers of the spheres. And in that case, the magnitude of the force, it's the same force, right? This is Newton's third law. Those two forces have to be equal and opposite. That magnitude force is a constant, which we're going to call capital G, times the product of the two masses, right, that are pulling on each other, divided by the square of the distance between the centers. And capital G is a rather small number, and that tells us why gravity is so weak at the everyday scale. 6.67 times 10 to the minus 11 in SI units. And what that means is, if I take a 1 kilogram mass and another 1 kilogram mass and separate them by a meter, this would be 1 times 1 divided by 1 squared. Then we have to multiply by G. If we multiply by G in SI units, the right-hand side would be 6.67 times 10 to the minus 11, and it would be in newtons. So the force between 2 kilogram masses at meter separation would be 10 to the minus 11 newtons. It's kind of scale. I've graded out the units associated with G because you can actually back out the units of G by looking at this relationship. I know, like all equations in this class, that this is a dimensionally balanced equation. Therefore, if I put all SI units into everything but one thing, I know that the last thing I didn't put the units in for has to have the correct SI units in order to make the equation balance. So F comes in newtons in SI. These masses are in kilograms and R is in meters in SI units. So I can back out by solving for G in terms of those things what the units of G are. And they end up being newtons times meter squared divided by kilogram squared. But, you know, to know the number in SI units is good enough because we can just throw it in. As long as we're using all SI units, we know the SI unit that's going to come out. Okay, just a first introductory example. With what force does Earth pull on Moon? Well, I'm just going to plug directly into the formula, but I've got to look up some of these masses, and it's a little bit confusing to think about, well, how do we know the mass of Earth? How do we know mass of Moon? How do we know the distance between the center of Earth and the center of Moon? But let's not worry about that right now. We can look them up in the back of our book, or we can Google them. Earth's mass is 5.98 times 10 to the 24th kilograms. Moon's mass, 7.35 times 10 to the 22. And the distance between their centers, 0.385 times 10 to the 9 meters. So those are all really big numbers. This is the point at which you want to be careful that you know how to put scientific notation into your calculator, because we're going to be using a lot of scientific notation here, and you want to make sure that you're doing that right in your calculator. So we put that in here along with the capital G constant and put those all in. You can just check. Try doing this calculation in your calculator and make sure you end up with the force approximately 2 times 10 to the 20th newtons. A huge force. Well, of course, Earth, you know, the moon is huge, so we got to pull on it with a huge force to keep it going in a circle. It's sort of so big that we can't fathom how big it is, but that's 2 with 20 zeros after it, that many newtons. Well, okay, it's got to be huge. Okay, I want you to do an introductory kinds of calculation. This was only half a step more complicated than one we just did together. A 4-kilogram object attracts another object gravitationally with a force of 2.5 times 10 to the minus 10 newtons when they are 1/4 of a meter apart. Let's assume they're spheres, and this 1/4 of a meter is the distance between the center of the spheres. Can you find the other object's mass? In this case, we know the force, but we want to solve for one of the masses in Newton's law of gravitation. So try to do that, see if you can figure out what it is, and we'll do it together when the next video starts.